Can you hear me? Yes. Okay. Hi. Let me first be redundant and thank Henry and Krishna for inviting me. So to be worthy of this workshop, you need to have a cool application and interesting theory. So I hope I put it on the title. I hope the talk will convey both. Okay, so let's start with the application. Genomic data is becoming very hot. We all remember COVID. We use the genomic analysis to find viruses, but we expect this to blow up significantly soon with the advent of personalized medicine. Basically, the everyday medicine of medical treatment of ourselves will use genomic data and fancy analysis on it, and then we will have a blow up of this type of data. So why is it an interesting data in particular, unlike other data? Two features. The first is the nature of the data itself. It's very redundant. When we sequence some genomic data, it's not really new. Most of it is existing in other individuals, and we mostly need to convey this 0.01% that is new. So we must exploit this redundancy to get efficient handling of the data. The second is more about the format or media of this data. We don't actually get sequences as we hoped. As we hope, we get some reads because of the sequencing machines that we are using. And that makes our life harder. As you will see in this talk, it will we'll need to have more stuff into our coding scheme. And basically, this is very similar to DNA storage. They have the same, because they use the same machines, they have similar issues of getting grids and not sequences. But the main difference is that we here in this talk, we don't control the data. In DNA storage, you can encode the data. Here, the data is from biology. We cannot control what's there. We only know that it's redundant. Okay, so let's look at a typical system, communication system that communicates genomic data. We have a doctor's office that gets our DNA, and it needs to communicate it to the cloud because the processing is very heavy. It cannot do it in the office. It needs to communicate to the cloud, and it does it over the noise-free internet. It's basically a noise-free communication, but because this data is huge, we talk about tens of gigabytes, and also with some duplications. The problem of compressing the data is real. We really need to do it to be viable over the internet. That's a communication setting. We have a similar setting in storage, where instead of communicating it over distance, we need to communicate it over time. Suppose we sequence many patients, but only a few of them, maybe one patient J, we actually need to process it in the future. And since we don't know at the time of sequencing who will be this J, we need to store all of them so it's ready for future processing, and we need to compress the data because we don't want to spend too much money on this storage system. So it's a very similar setting, only in storage instead of communication. We also need compression here. By the way, if you have questions, stop me. It's more like an informal talk. Okay, so why these reads make our life hard to compress? We cannot compress them individually. It's not efficient to compress short sequences. And also, we don't get any information like context of those reads from the sequencing machine to kind of place it over the long sequence. So we have difficulties. What are the state-of-the-art solutions that people actually do compression? Here you can choose. If you want to use a reference, then you need to invest a lot of work in aligning those reads over the reference such that you can communicate their context, their position. But that's a lot of work. Another option, if you don't want to use a reference, then you need to do some clustering to group together somehow similar reads, and then you get the benefit of similarity to compress them. But that's also very heavy in computation on the encoder. And we think about a doctor office that needs to run those complex encoders, it may not be economically viable. So in this work, we try to avoid high complexity encoding. Okay, so how would we do it? Basically, we take a reference. The reference will help us using this high redundancy, such that we only need to convey the differences. And what we do for complexity, we remove the reference. We don't put it in the encoder. We just do a decoder-only reference, decoder-only side information. And there are two benefits. One is the complexity. We basically free the doctor from handling the reference with all the complexity using a high storage cost. And also there's a privacy benefit. If we want to sequence Jane at the doctor, we have Jane's sister's DNA at the cloud, but Jane's sister does not necessarily want Jane's doctor to see her DNA. So with this scheme, we don't have to, we have better privacy. Okay, so now we can define the problem for these settings. We want, given an input, the input is a batch of reads, M reads, each one is called the XI. We want to have a coding scheme, a compression scheme, that has 4 parameters: the number of reads, the length of each read, the rate, basically the ratio between the output of the encoder, output length of the encoder to the input. It's a number smaller than 1, and the probability to succeed, it's a very high number to get back the exact batch of reads at the decoder, same as we had at the encoder. So you can think of that as a quasi-lossless compression. We do have some probability of failure, but when we succeed, it's everything. It's an exact reconstruction of all the reads. Okay, so that's the problem. We do have a solution to the problem in the form of code construction with 4 layers. I will not get into what each layer does, but the interesting part is the analysis. Each layer has some parameters, and we want to analyze and optimize those parameters to get p-success that we want at a low rate, the lowest rate possible that we can. I was tempted to talk about that, but because you are a special audience of theoreticians, instead of talking about a solution that we have, I'll talk more generally about the problem that we have. So to see the problem, let's look first on the classics of coding theory. Here we have classical communication over a noisy channel. Here we have also a classic, which is a source coding with side information, where the error channel is replaced by a difference channel. And now the similar decoder that we have here is operated here, but in a different way. It has some reference, some side information, and it uses Y and some information from the encoder to reproduce the input to the encoder. That's also a classic. What we have here is some variation on that, where we cannot just use it as is. We need to add something else, because what we get as input is not the individual fragment that is similar to the input, but we have only this long, very long sequence Y. So we need this aligner to tell the decoder which part of capital Y it needs to use for the reconstruction of the original read. So that's the problem that we do here. By the way, any question? Okay, so just to make sure we understand the basic term that I will use a lot, the term reconstruction. It's, as I said, it's a different way to use a decoder of an error-correcting code. This is the input, Y. And what the decoder does, it looks within some sphere of radius P for a source input, the source input that has some syndrome or coset or a color indication that it got from the encoder. So the encoder told the decoder orange, so it looks within the sphere for an orange vector, and this would be the output of the decoder. And from the properties of the error-correcting code, we can guarantee uniqueness so long that X is actually close enough to y.
Are you thinking of doing this on like a read kind of basis, or doing it like all the reads together?
Okay, so that's a classic. It's assuming we get the small y, the lowercase y. That's only an intro to our problem. Our problem is more difficult because we get the long y. We don't know where. But that's just the basic of what reconstruction is.
Okay.
More questions? Yeah, that's a classic scheme. Now the problem we have is we want to reconstruct xi. Xi is one of many reads in the batch. And we only have this long y. The problem is to know which part of capital Y will help us reconstruct xi. We need to find a similar part. But you probably notice that we have some chicken and egg problem. We want to reconstruct xi. So how can we tell what is similar within y to that xi? So that's the paradox that we have to solve. And the way we solve it is using some function. Part of the encoded information is this f of xi. And what we do, we'll use this function of xi to find the similarity. We basically want to partition the subsequences of y to useful for reconstruction and others that are not useful. And for that, we need some hint. And as you can see, the problem moved from being a deterministic problem of knowing whether it's good enough for reconstruction to something more non-deterministic or probabilistic. Now we can only tell that some part of y is likely useful for reconstruction. Now, the way we define it information theoretically is we say that for every xi, there is one particular position within y that is the native position. And between that yi to xi, there is some useful channel with parameter p, while all other positions, they have some useless channel to that x, and we really don't want them. They will not help us reconstruct, so we want to not find them in our alignment. We also have the term proper. We call this special yi the proper alignment, and we hope to find it with high probability. And all the rest, for example, this is also part of the alignment, the output of the aligner, and this is improper because it's not really useful. It's basically a false alignment that we want to minimize its occurrence. Okay, to be concrete, let's look at substitution-only differences. And then you can probably guess by yourself that what f should be is some sample. We have a sample of the read that we include in the encoded message. And now we can decide whether some alignment is useful or not, or at least useful or not, is by some thresholding. We look for every subsequences yij that have a small enough Hamming distance to the sample that we got from the encoder. And if we have this threshold, if we're below, we say it's a good alignment. If we are above, we reject. And for example, for substitutions only, we can use a symmetric channel as the model. Here we have symmetric channel with probability p, and here we have a useless symmetric channel with probability q minus 1 over q. But as you can see, this threshold will have two roles. If we increase t, we'll get more proper alignments, but at the same time, we'll get more improper, undesired alignments. So we need to be careful about how we set this t. Yes?
So this, what you are sending, this lentil sample of xi, does it also have the location of the entries? Meaning
it's agreed upon. So the positions are known to both encoder and decoder.
All reads.
Yes. Okay, so now we want to move away from substitutions only and also consider single deletion. So now we allow in each read a single deletion between y and x. Remember, it's a difference channel. This is not a real channel error. But in addition to one deletion, we want as many substitutions that we want to specify. We call this model SDMS, single deletion, multiple substitutions. That's a useful model because it also allows deletions. And the question is, how should we now align for this type of errors? Let's look at existing options. One way is to use the Hamming distance, but that's not a good idea. Now with the deletion, you can see two sequences that are very dissimilar in terms of Hamming, but it's clear that if you remove, you delete one bit, you get very similar. So it's not a good idea to use the Hamming. Maybe the most natural choice is Levenstein, but that's very high complexity. We need to compute it. It's not linear time. It's some dynamic programming, and we need to run it for each offset within the reference. Another existing option is called the shifted Hamming distance. I'll not get into how it's computed, but basically we have some end here. So we take the Hamming distance, but we want, in order to declare a difference, it needs to be different both in original alignment and also in one shift. That's a very good in terms of complexity. It has linear complexity, but as we will see soon, it has a very high rate of false alignments. What we suggest instead is a new alignment distance that we call the shift compensating distance. Again, I will not get into exact details of the function, but think of those phi's as the cumulative distance function. Cumulative means that we have t here, and we take phi. Let's look at the specific case for a single deletion. We take phi1, and the maximum, we need to maximize this function over t between 0 and n, and that will give us a number, and that number is how far x and y are in terms of SDMS. So we propose that. Let's see why it's a good idea. Let's first see a graphical example. Basically, we have this phi0 in blue, phi1 in orange, and we look for the maximum, the position where they differ maximally. We declare that, and as you can see here, it's not a coincidence because that's a good, this maximal position is a good indication of where the deletion happened between y and x. So that's a graphical intuition. Now what the main result we have in the alignment part is we derive the exact distribution of that distance over two sequences that are unrelated. We want to find the false alignment, so we take x and y that are unrelated, they are random IID independent sequences, and we want to find the probability for each value of this distance. So we have a closed form expression for the distribution, and here we have some combinatorial expressions. They are not important, but what's important is that we have a closed form. So let me give you the idea of that proof. Basically, when x and y are random independent, we can think about this delta function that we defined as part of the computation of the distance as a random walk. With probability half, it stays in the same position because both phi1 and phi0 have the same value. Probability quarter each, it goes up or down one position. You can see here. Here it's an example of that random walk, but for structured x and y. X and y here are related. One is obtained from the other using a deletion. But here you have a random walk that is unstructured. It's random. And now that we know that it's a random walk, what we need to do to calculate the distribution is to find given two parameters, t star and m, we want to count how many random walks we have that attain their maximum of m at time t star. And you can see this maximum is very reminiscent of what we had here, because that's what we maximize. So if we can determine it for any m and any t, we can find the distribution. There's only one piece left here, is that this random walk does not represent a unique pair of x and y, sorry, a unique pair of phi1 and phi0. We also need to count how many pairs of phi1 and phi0 map into each type of random walk that we have here. So that's also some counting that we need to do, and it explains the complex counting expression. But the good news is we have the exact counting of that. Now, using that analysis, we can now compare our new distance to the existing distance, which we have in green. What we see here is the CDF of that distribution. And the way to look at it is, suppose we pick some threshold that we need for the proper alignment, let's say 4. And now we want to compare the two distances in terms of false alignment. So what we see here is that our distance in probability less than 0.10 will false align, given that threshold, but the competing distance, more than half of the times, more than half of the offsets will declare that good alignment, which is very bad. So you see this tells us the advantage. Another way to see it is we took some length 150 random binary sequence, and we took, starting that offset, the subsequence, and we deleted 1 bit. And now we slided that subsequence over the entire sequence, and we compare the 3 distances. You see that if we take the Hamming distance, it will not detect that it's actually taken from there. That's only a blip compared to the random, the background level. The existing distance does do a good job in the correct alignment. So it does tell us 0. It tells us, yeah, it's related, very related. But you can see it's not very distinguishable from the background, while the new distance does both. It does tell us 0, but you see that we have bigger margins from the background, which is exactly what we want from such an alignment. Okay, so after we talked about alignment, let's go back to the reconstruction. And now we probably observed that we took the encoder and split it into 2. One part we only use for alignment, and the other part we use for reconstruction. And the question is, can we maybe reuse some of this information to use in both alignment and reconstruction? And potential savings is clear, it's a rate. So let's see that we can actually do it. And for that, let's talk about reconstruction for the same error model that we call SDMS. So let's look at
So the syndromes of Xi, they are computed from a linear code. What is?
Yeah. We can see that exactly the idea that I'll show now will help us use standard linear codes also with deletions. We'll see how to do it shortly. But let's look first at the channel coding problem of correcting SDMS. So we have the input, then we delete this bit, underline bit, and add a bunch of substitutions. And now we need a decoder, a code and decoder to get us back to the original input. If you want to talk about the source coding, the problem is not much simpler, not much different. The only difference is that now we get the side information, this Y, and this syndrome. And we need to use a similar decoding, maybe with the same code, to get back to the X, to the orange. That doesn't help. But what does help is now we recall that we have this sample, this F of length L of X, and we go back to what we saw in the distance, is that this F didn't just give us the number, which is the distance, it also gave us some estimate on the position of where the deletion happened. And now we will use exactly that to get a simpler correction of that deletion. So how will we do it? Here I skip some technical detail that we need to adjust the distance that I mentioned before to using over FL, because before I used it on the full segments. But once we do that adaptation, the T star that we find in the maximization give us, with some uncertainty, a good estimate on the deletion. So if we found that this is the T star, then deletion can be in any of those between this orange and the next orange, not including. And now we can use that information. If before we didn't know anything about the deletion, as happens in channel coding, nobody tells us anything. Here, this sample will give us some hint on the deletion. And now what we can do, instead of just plugging in Y to the SDMS decoder, as we would do in channel code, we will take Y and expand it to all deletions, basically shrink Y, delete different options according to the candidate list that we got from here, and put each of those into a substitution-only decoder. And because of that property, that a small error in the deletion position will only give us a small number of extra substitution. The red here are extra substitutions that we get from misestimating the deletion. These are not the real substitutions that we have in addition, but as you can see, we have few reds so long that our ambiguity is small. And now we can translate that small ambiguity to a few added substitutions, so we can correct those with maybe a little stronger substitution-only decoder. Okay, what we do is we actually have a decoding algorithm to exploit it. What we do, we take this Y and expand all the options that we suspect of deletions. Here we have a wider. And what we basically decode each one of them for substitution only and take the majority. And we see that the correct one actually was in the majority, and that's why we get correct decoding, even though some of them are returning the wrong input. Questions? Okay, so to summarize, we have a new problem. We have some coding scheme to help it, but maybe not the last word on it. We can improve it. And the alignment algorithm are a very important part of the coding scheme. Something about the future. So one thing is the alignment. Yeah, basically we have a way to extend the distance that I mentioned to not just one deletion. We can do any number of deletions, but that's no longer linear time. Now the maximization is no longer linear time. What we found is that empirically, we have some approximation that works well. So the question is, can we do some theoretical analysis on that? And that's how we can extend it to multiple deletions. But if you think that this is maybe not coding theory, it's only alignment, then there are problems also for the actual coding theory, for the actual reconstruction, because now the alignment gives us multiple possibilities to reconstruct. The way we handle it currently in our scheme is we do it individually. We decoded first Y1, first Y2, and only if exactly one of them succeeded, we declared success. Otherwise, we declared failure. But the real problem, we should do it jointly. We should somehow devise a decoding algorithm that gets multiple reconstruction candidates and somehow finds the most likely candidate given all the information that we have. So designing such decoding algorithms is a useful and something within the coding theory realm. Okay, if you want to read more, most of the things I said and skipped are in this paper that shows here. If you don't have to read the paper, if you have ideas, you can talk to me here outside. So thank you very much.
We have time for a couple of questions.
So the problem of alignment goes away if Y is available at the encoder.
Yes.
I didn't understand the motivation for why we cannot have Y at the encoder. Because if I recall correctly, you said the size of the genome Y is a few gigabytes. This is not much at all in terms of storage.
No, it's not just one. You need Jane's sister and Bob's sister, Bob's brother. It's multiple.
Isn't it like 99%, 99, but even more? We don't need the exact family members, right? Any human.
Right. Then if it's less similar, you need a stronger code. the cost of compression will high. But the short answer to your question is here. Our code, our encoder is basically a simple matrix vector product. No need to align, no need to run any time-consuming, resource-consuming operation at the encoder.
Yeah, so that was my follow-up question, that what is the complexity that you're talking about? Is it like, can it be run on a single GPU? Or?
Yeah, the encoder is trivial.
No, suppose you also do, if you have a reference.
The encoder, that's the prior schemes, and they are extremely heavy. You cannot do it in a small doctor's office PC. It doesn't scale.
Thank you.
I have a question about, like, I think DNA is known to have lots of repeats, like regular repeating patterns, this kind of thing. And it seemed to me that that might allow you, or might cause you to miss, like in this section. But then maybe that doesn't matter because it's still a good reference. I don't know if you've thought about that.
Yes, so the current analysis that we do assumes those channels, probabilistic, relatively simple channels, like a BSC. But you're right that in real data, you may get different types of similarities. So if we know something, you can improve the scheme.
No, I mean, like, there's like, DNA has this like ATG, there'll be very regular repeating patterns for one thing. So like, if you sample a part that's a regular repeating pattern, you're gonna find matches in lots of places. And in your analysis, you might call that an error, but it's not clear. I'm trying to say, does it affect your decoding, or maybe that's just fine because it still provides decent side information?
Yeah, you're right that we did this assumption that there's only one useful.
Yeah.
But if the reality is, as you say, things will only improve for us. It will not hurt us. If we have more good options, then maybe something we called improper is actually useful.
You can make it longer, I guess. Also, you can make it, the X's can be longer up to where you don't see that very low repetition. Should help, right?
Yeah, it's an interesting comment on how to decide the size of the read. One way is about this single deletion. If you only want to deal with single deletion, you want the read to be short enough so most of the time you only see one. But if you don't have this issue, yeah, increasing the read size will help us. Okay, more questions?
I have a question which is not directly related to this. So if you have side information which has only substitution errors, then we know how exactly to do the distributed source encode, right? Like the discuss before. But if the side information is my source but one bit deleted from the source, do we know what to do in this case exactly? Do we know the
So the straightforward answer is to use a code that can correct it.
Right.
But that's not easy. Those codes are not as convenient as linear code. That's why we offer this alternative solution using those hints on the deletion position.
I was curious if that's the standard approach of doing this so far at least. Or
There's no standard. I'm not aware of prior attempts at that problem.
Thank you very much.